So this video refers to Lecture 5 of the Statics module, Equilibrium of a Rigid Body, and you can follow it with the PowerPoint that's available on the website as well. I suppose the first thing to do is consider what is equilibrium. So this will be the introductory video to equilibrium of a rigid body, and what we're going to do is we're going to very quickly, I'll talk through a couple of cases of what it is and some things you'd look out for in the diagrams. Then in the later videos we'll look at some specifically defining two-force members in the next video, and then in the final video we'll look at some support reactions and applying equations of equilibrium. So if you look through the first few pages and few slides of Lecture 5, there's a lot of different real-world applications, but then we end up with a picture that looks something like this. We have a particle or a rigid body. There's lots of forces acting on it, and the idea of it being in equilibrium is that the sum of the forces is equal to 0, so there's no net effect, and also for it to be in equilibrium, the sum of the moments about a point has to be equal to 0. So it's not moving, it's not translating in any direction. Sum of the forces is 0. It's not turning in any direction, it's not rotating. The sum of the moments is also 0. That's the definition of something being in equilibrium. So you may have to start to work out what forces are required at certain points to hold it in equilibrium. And we're going to have to work on free body diagrams that we did previously. And what we'd do is we'd draw a free body diagram. We have to examine very carefully the pictures that are being given to us to work out where forces are acting. So there are examples of this in the lecture notes, beginning on slide 9. I'll try and draw a couple here though. So for instance, the sort of detail you may be asked to distinguish between is that. So on the left hand side we have a rolling joint, and on the right hand side we have a pin joint, and the rolling joint is a bit like a roller skate. So if I push down on it, then it will push back up. If I push it in the X direction, so if I pushed on it that way, it would just roll. There'd be no back force, there'd be no reactional force, so there's no support, there's nothing to stop it moving in the X direction. In the case of the pin joint, if I push down on it, it'll push back up, there's a support reaction there. If I push it from the side, you can see it's fixed to the ground. So if I pushed it from the side, if I applied a force to it that way, then it would be able to push back. So there is a support reaction there. So that's just one example of the sort of detail you might have to look at when you're considering taking your applications, your diagrams from questions, and putting them into free body diagrams. Slide 10 and 11 have several different examples of that, including the ones that we've got there. So they've got cables, they've got rollers or rockers, which are similar, there's just different ways of drawing them. There's some sliding joints. We've got the pin joint on top of slide 11, some more sliding joints and a fixed support, and it gives you ideas and it shows you where the forces are acting and where the moments are acting in each of those. I'm not going to redraw those because you're able to read them and inwardly digest them yourself, but if you do have any questions you can email me about them. So if you look at the first example is a picture of a pedal for like a brake pedal, and there's some kind of lever attached and there's also a spring attached, and we're going to want to eventually draw a free body diagram. So what we do is we draw our free body diagram like that, and that's very badly drawn, I know. Now as I push on the pedal with my foot, this is referring to the photograph from slide 12. But as I push with a force on the pedal, what you can't see from my picture, my diagram so far, is there is actually a pin joint there. So we're going to have some forces acting. Now in the picture there is a lever acting up here, a link of 100 newtons. Okay, so I push down on the with force F. Then there's also going to be something trying to pull it back that way, trying to resist that force of 100 newtons. It's also going to be the spring that's trying to resist that force. It's being stretched by 37.5 millimeters. It tells us in the question, and we've got a spring constant in the diagram. And that spring constant is 4 newtons per millimeter. So the force is going to be 4 times 37.5, which is 150. But we've also got some other forces, some reaction forces, which I'll just draw in green because these are the new bits for today. We're going to have, because it's a pin joint, force in the y direction, and we're going to have force in the x direction. And you could label them AY and AX. We're calling them A because this is point A, labelled in the original diagram. So that's the new bit for today, is thinking about reaction forces and adding them to the diagram. Your question that for you to practice that goes with that is given on slide 15 of the lecture. So if you pause this video, you're not being asked to solve anything numerically. You're just being asked to draw some free body diagrams considering the joints that are shown in the initial question. So there's 2 to practice, one beginning on slide 15, one beginning on slide 17, and if you pause the video, have a go, and then I'll come back and show you how to draw them. So you should have had a go at the first group problem solving exercise of lecture 5, which is drawing a free body diagram considering all the different forces that are taking place in there. So if I do a very, very brief sketch, we've got something like that, and we know that there is a tension in a cable coming from B. So that's point B here, wasn't it? And we know the angle of that is 5, 12, 13. And we know, this is very badly drawn, but we know that this bit here is going to be 5.4 metres, and this bit here is going to be 3.6 metres, so you can see it's not to scale already. And we know that there's a force acting down here. I should draw my forces in different colours, so let's use green. There's another force acting down here, that's 6,250 newtons, and you've got that because you've got the you've been given the forces in the actual question. We've also got the weight of the arm itself. So the weight of the arm itself with the boom was 3,250 newtons. It's given you point G, so point G is somewhere about here. And it's asked you to draw your free body diagram, so we are missing 2 different forces on here. We're missing AX and AY. And that was it, that's your free body diagram for this question. Apart from I've missed one small angle. I forgot to label my 30 degrees that I was given in the question. But that is your free body diagram for the first group problem solving question. If you pause the video, have a go at the second group problem solving question, beginning on slide 17, and then we'll come back and I'll show you how to do it. So you should have had a go at the second group problem solving exercise of lecture 5, beginning on slide 17 with a member ABC. And you were asked to draw the free body diagram. So if I sketch out roughly what we had to start with, we didn't have that at all. So we've got D, we've got C, we've got B, we've got A, and here we've got a rolling joint, and here we've got a sliding joint, and we've also got a force acting here, 2.5 kilonewtons, and we've got a pin joint just there. We've got, that's at 60 degrees, and we've got a moment about B of 4 kilonewton meters. We're asked to just draw the free body diagram for what's happening there. We've also got 45 degrees there, and 3 metre distance there. So that's the diagram you were given, roughly. Bits we're not going to need in a free body diagram. If we're only drawing member member ABC, we're only going to draw everything that's happening in there, A to C. And we're going to have to label some forces in this. So at point A, all we have to do is label reaction forces. Well, at point A, the sliding joint is free to move that way. So in that orientation there's nothing to resist the force. So in that orientation there's no reaction force. If I push on it here, it doesn't move. If I pushed on it that way, it wouldn't move. So in that direction there is a reactional force, a normal force. So we can label that. We'll label that NA. Put that there and label it NA. I've got my rolling joint at B. Can't tell it's a rolling joint from the way I've drawn it, but it should be a rocking joint or a rolling joint. If I were to push it, so if I were just imagining joint B on its own, if I were to push it that way, it would just fall over. If I were to push it that way, it would just fall over. So in those directions there's no resistive force, there's no reactive force. If I were to push down on it from above, then it would support its own weight, it wouldn't sink through the surface it sat on. So there is a reactive force at B. And at C, there is a force pushing from C to D, because D is pinned. So at D, there must be some kind of force here, which means to keep the bar solid and not breaking apart, there must also be a force here. So there is a force going from C to D. As I say, everything beyond C, so everything that side of the orange to the right side of the orange line, you wouldn't need to draw. You would have your 4 kilonewton meter. You'd have that label for the moment, but you wouldn't have to draw anything else. So that would be how you'd draw your free body diagram for the second group problem solving exercise of lecture 5. So to summarise that, we can take real world applications. We can they can be 2-dimensional or 3-dimensional. We'll look at some of those later. But just in terms of 2-dimensional, we can resolve all our forces and our moments. And in order for a circumstance, a situation to be in equilibrium, then its sum of its forces in the x and its sum of the forces in the y direction must equal 0, and its sum of the moments about a point must equal 0. That's a 2-dimensional situation. When we scale that up to 3 dimensions, so 3-dimensionally, we have to add sum of the forces in the z equals 0, sum of the moments, I missed my sum out here, sum of the moments in the y, and sum of the moments about the z-axis equals 0, and this 0 here would change to an x. So we change from talking about moments about a point to moments about the 3 coordinate axes. So in 3 dimensions, for it to be in equilibrium, all of those 6 equations have to hold true. That concludes the first introductory video to equations of equilibrium. The key point for it is from this is to make sure you're aware of the different types of joint that exist, how you interpret those, what reaction forces are taking place at those joints, and that's summarised on slides 10 and 11 of lecture 5. And if any questions arise from that, if you just email me.